In this video, we're going to be looking at the Introduction to Organic Chemistry, and these are the double outcomes as part of the IGCSE chemistry course from Edexcel. So we're going to be looking at what a hydrocarbon is, how we can represent these molecules using different types of formula, what is meant by the terms homologous series, functional group, and isomerism. We'll also be looking at how we name compounds and how we can write the structural or displayed formula if we're given a molecular formula, and also how to classify basic organic reactions. Now, this is just an introduction to the overall topic. What you'll find is you'll go into more detail and potentially repeat parts of this video when you're looking at the alkanes and the alkenes in more detail. So this is just an overall of organic chemistry. So when we're talking about an organic compound, what we mean is a carbon-based compound. Now, there are a couple of exceptions. For example, carbon monoxide, carbon dioxide, carbonates, and hydrogen carbonates are not classed as organic compounds, but everything else will be. So carbohydrates, hydrocarbons, alcohols, alkanes, alkenes, these are all carbon-based compounds, so we call them organic. And organic compounds can exist as a straight chain, they can exist as branched chains, or they can exist as rings of carbons, and they will always then have hydrogens attached to them. Now, we're not going to go into a lot of detail about the ring structures at GCSE, you cover that at A level, but we're going to look at the chains and the branched chains. Now, the most simple organic compounds are hydrocarbons. And this is a definition that you have to memorise because it does come up in exams and it is a 2-mark question. And the reason that it's a 2-marker is that hydrocarbons are molecules that contain carbon and hydrogen only. And you get a mark for specifying only. So typically this would be the 1st mark, and then the only would be the 2nd mark. So please make sure that you are very specific with that definition. It does come up very regularly. Now, the carbons themselves can be joined using single bonds, double bonds, or even triple bonds. Now, we're not going to go into too much detail about the triple bonds, but they can exist. We're going to put our focus on the single and the double. The hydrogens that are part of these hydrocarbons are bonded to the carbons using only single covalent bonds. Because remember, hydrogen only has one outer electron, so it can only form one covalent bond. And in this case, it would be bonding to the carbon. Now, all of these families of compounds that we are going to meet are known as a homologous series. So a homologous series is another word for a family of compounds. And we're going to use this analogy of being a family when we talk about how we name these substances as well. And we'll look at that later on in this video as well as in further topics. So a homologous series is defined as a series of compounds that have similar chemical properties. They are represented by something known as a general formula, and we'll go into more detail about that soon. They also show a trend in their physical properties, and they share the same functional group. And when we're talking about a functional group, we mean something specific to that molecule that gives it its characteristics. So some examples of some homologous series that you will meet will be alkanes and alkenes. Triple students and A-level students go into detail about alcohols, carboxylic acids, and esters. So these are just some more homologous series. So they're a family of compounds. And each member of the group all share the same functional group. And an example would be something like an OH. So every single alcohol is going to contain this group. And it's this OH group that gives it its properties. So it is what defines as an alcohol, is to have this group. And as you increase your number of carbons, or you go from each member, they differ by CH2. So every time we add in 1 carbon, we also add in 2 hydrogens. And we'll look at how that's possible when we start to look at the formulas. Now, there are 5 different types of formula that you should be able to write for each of the molecules that you're going to meet. So we can have empirical formula, which is the simplest whole number ratio. We can have the molecular formula that shows the actual number of atoms. We can have the general formula that represents the composition of any member of the homologous series. The structural formula shows how the molecules are joined together, and then we have the displayed formula that shows all the bonds in the molecule. And we're going to look at an example of how to do this. So we're going to look at two different molecules. One of them is known as butane and one of them is known as butene. Now you won't have met these before, and that's okay. You're going to go into more detail about them when you cover alkanes and alkenes, but I will give you the basics of what you need to know to understand how we then write out the formulas. So butane is an alkane, which means it has only single carbon-to-carbon bonds, whereas butene is an alkene, and that contains at least one carbon-to-carbon double bond. So what we're going to do is we're going to write out the displayed formula first of all, and then we'll work our way back. So when we have this but, that tells us that we have 4 carbons. So I'm going to draw out 1, 2, 3, 4 carbons. Now, because these are all single bonds, I have no double bonds here. They are all on their own, and now we want to make sure that each carbon has got a total of 4 bonds, and we do this by filling in the hydrogens. So we have 1 hydrogen, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And that is our displayed formula. Now, when we're going to structural formula, what we do is we take that displayed formula and we just shrink it into smaller chunks. So what we do is we take the first part, which is a C and 3 hydrogens. Then the next is CH2, another CH2, and then CH3. So I'm not showing all the bonds this time, but I am still showing what each of my sections or little chunks are. I'm going to jump to the molecular formula, and that's simply where I just count up the number of carbons and the number of hydrogens. So this is C4H10. Now the general formula is a formula that's used to work out the molecular formula for any member of the alkanes. And you will go into a little bit more detail about this when you look at the alkanes, but it's CN, where N is any number, and then to work out the hydrogens, you multiply the number of carbons by 2, and then you add 2. And we can see that is the case here, because we have 4 carbons, we multiply that number by 2 to get 8, plus 2 is 10, and that gives us our molecular formula. Now the empirical formula is to take the simplest whole number ratio of that molecular formula. So this is just the same as ratios that you've met in maths, where you want to get it down to the most simple number. So we wouldn't write 4 and 10 because both of these numbers can be divided by 2. So my empirical formula for butane would be C2H5. Now for butene, we have at least 1 double bond here. So what I'm going to do is I'm going to start again with my displayed formula, and I'm going to draw my 4 carbons, and I'm going to form a double bond with one of them, and I'm just going to keep it at the start here. Now I do the same thing, and I make sure that all the rest of my carbons have got 4 bonds, and I do this by adding in hydrogens. So I have 4 bonds there. Notice that that carbon already has 2 bonds. The next carbon already has 3 to each of the other carbons, so that only needs 1 hydrogen. The third carbon needs 2 hydrogens, and then the last one needs 3. And what I'm going to do is I'm going to write out my structural formula, which is CH2, and then I show my double bond. I then have CH, CH2, CH3. Again, my molecular formula this time, I'm counting. I've got 4 carbons again, but this time I have 8 hydrogens. So my general formula is CnH2n. So this time I'm just multiplying the number of carbons by 2 to get my number of hydrogens. And for my empirical formula, I want to write this in the simplest whole number ratio. So again, both of these numbers can be divided by the same number, and this time it's 4. So I can write CH2 as my empirical formula. Now, some of the hydrocarbons that we will meet will not be straight chain, meaning they will not have all of the carbons in a row. Sometimes they have side branches or side chains, as they're sometimes known as, on them. And the two side chains that you may come across at IGCSE will be a methyl, which is a CH3, and very rarely, but sometimes, an ethyl, which is CH2CH3. So this molecule here is an example of a branched hydrocarbon, meaning that we have our 3 carbons in the center here, and then we have this branch coming off it at the side. So this is our side chain, and in this case it's a methyl. Now, because we can have these branched chains that can still have the same number of carbons and hydrogen as another molecule, we have to give every individual hydrocarbon a specific name. And to name a hydrocarbon, we use something known as the systematic naming method. And the rules for this were developed by the International Union of Pure and Applied Chemistry, or IUPAC. And the rules are very simple, and if you follow the steps each and every time, you will get the correct answer. And they are based on the number of carbons in the molecule, whether or not there are double bonds, what the side chains are, and where the side chains are located. So this is how you do it. You do 4 steps. Firstly, you identify the longest continuous chain of carbons. So the easiest way to do that is start at one end of the molecule and count until you reach the other end. And you may need to do this 2 or 3 times because the chain may twist or may change direction, and you want to make sure then that you have the highest possible number, and that's your longest chain. Then what you want to do is you want to number the carbons, and that's just simply number them 1, 2, 3, and so on, but you have to do it so that the branch or the double bond is on the lowest possible number. So you want to make sure that your branch is not on potentially carbon number 6 when it could be on carbon number 2. So we always want to make sure it's the lowest number. We then identify the position, the number, and the type of branches that we have. And then we name the structure starting with the branches and then the length of the alkane chain that is the basis for it. Now, what you will find is that you will do this more and more throughout organic chemistry, and the best way to get good at this is to practice. You will find lots of examples on the internet or from your teacher about naming of hydrocarbons, and it does come up very commonly in exams. So let's have a look at a couple of examples. So the first thing that we need to do with this one is we need to start by identifying the longest continuous chain. And luckily for us, it's just the one that goes along the centre. Now we're going to number them, and what I always suggest you do is you number them from left to right and right to left. And then you can decide which numbering you need to use, and that helps you figure out the positions of the chain. So we're going to number 1, 2, and 3. And then 3, 2, 1. Now in this case, our branch is a CH3 branch, and regardless of which way we number it, it is going to be on carbon number 2. So that doesn't matter. So my first part of the name is going to be a 2 to tell me that I have a branch on carbon number 2. I then name the type of branch, and that is a methyl. And then I name my alkane. And in this case, it's got 3 carbons, so my basic alkane with 3 carbons is called propane. So this molecule is 2-methyl-propane. I then do the same thing for this second example, so I want to identify my longest continuous chain, and that's the 4 carbons in the centre. I'm then going to number 1, 2, 3, and 4, and then 4, 3, 2, 1. Again, I have a methyl chain here, and I need to decide what carbon number this is going to be on. And this is where I compare my two numbers. So it can either be on carbon number 2 or carbon number 3. And we've said that we always want to use the lowest number. So in this case, we're going to be numbering our carbons from left to right. So I'm going to cross out the top ones because we don't need them. So again, I have a 2 to tell me that my branch is on carbon number 2. I have a methyl group. And then the name of the alkane that's got 4 carbons is butane. So this is 2-methyl-butane. If we look at another 2 examples, we've got an alkane and then this time an alkene. So we'll come back to the alkene in just a moment. We want to find the longest continuous chain this time, and the most common trap to fall into here is to simply go from here to here and say that the longest chain is 5 and that I have an ethyl group here. But actually, what we can do is we can go from here again and then count to here, and what I find is I actually now have 6 carbons. So my longest continuous chain is not the one that is horizontally across, it's actually going horizontal and then twisting and going vertical. Be aware that this is a possible trick question. They want to make sure that you understand that you have to count the longest continuous number of carbons. So again, we're going to number them. So we're going to have 1, 2, 3, 4, 5, 6, or 6, 5, 4, 3, 2, and 1. And again, we're going to see our carbon chain here is our methyl, and it can be on carbon number 3 or carbon number 4. We want the lowest number, so we're going to get rid of that numbering system and we're going to keep the bottom set. So my chain is on carbon 3, it is a methyl, and the alkane with 6 carbons is hexane. So this is 3-methyl-hexane. We then look at our alkene. This time I've got 4 carbons. I have no side chains here, but what's important for an alkene is the position of the double bond. We have to specify where the double bond is. And we will look at that in a little bit more detail in the alkenes topic. But to make you aware of how we do it, we again number 1, 2, 3, 4, or 4, 3, 2, 1. Now we have to focus on where the double bond starts. So we're going to have looking at this carbon here. So my double bond can either start on carbon number 2 or carbon number 3. So we again want the lowest possible number. So I'm going to get rid of the bottom set. And we say that this is but, meaning 4 carbons in my chain. And I have to specify that my double bond is between carbon number 2 and carbon number 3, but I always use the lowest number, so I use the 2, and this one ends in ene to tell me it is an alkene. So this is but-2-ene. Again, we will talk more about this naming system when we look at the alkenes in more detail. So another new term that we're going to be covering and go into more detail as we go through the organic chemistry is isomers. Now, isomers are compounds that have the same molecular formula but a different structural formula, because there is more than one way to arrange all of the carbons and hydrogens in these alkanes and alkenes. Despite them having different structures, they do all have the same molecular formula. So we call them isomers so that we can distinguish between them. So if we look at C5H12, we've got 3 different ways that we can actually arrange the molecules that have this formula. So if we have C5H12, we can start with having the 5 carbons in a row like that. And then I add in all of my hydrogens all around the carbons, making sure they are all single bonds, all clearly connected to 1, and each carbon has 4 bonds. And that substance is known as pentane. But what we can do is we can make this chain shorter and have 4 carbons, and we can have a side chain. So I could do 1, 2, 3, 4, and instead of having my 5th carbon on the end, I can put it in the centre, and that goes there. Now, your side chains cannot be on the end carbons. Your side chains must be in the inner carbons. It doesn't have to be right in the middle, but it has to be not on the first or the last. And then once I have that structure, I just put in all of my hydrogens all around. Again, making sure that each carbon has 4 bonds, and I completely surround the carbons. And that substance is known as 2-methyl butane. It's still C5H12, but it's just a different way to display it. I can do the same thing again, and I can make my molecule even shorter, and I can have 3 carbons as my main chain. I keep my carbon at the top that I previously had in the middle, and then now I add a carbon at the bottom. So again, I've put a side chain, but I still have 5 carbons. And then when I add in all of my hydrogens, I still have 12 hydrogens. So my molecular formula has not changed in any way. All that has changed is my structural formula. And this is known as 2,2-dimethyl propane. These 3 substances are isomers of each other because they are all C5H12, but you can see that they all look completely different. This is a typical exam question where it can ask you to draw out different isomers, so you might want to practice this, maybe ask your teacher for some questions, or see if you can find some questions online. Now we can also look at isomers of alkenes, and we'll go into a bit more detail about this when we go on to that particular topic, but the isomers of alkenes can have the double bond in different places, and as well as that they can also have branching the same way our alkanes can. So we can look at this time C4H8, and we can get 3 different structural formulas here. So the first one is to draw out my carbons all in a row, and because it is an alkene, at least one of these carbon-to-carbon bonds has to be double, so I'm going to put it right at the start. And then I fill in my 8 hydrogens, making sure that I am completely surrounding the molecule, but making sure that each carbon only has 4 bonds. So you'll see that we have a space underneath the double bond because we already have 4 bonds for our carbons, so we don't add any extra hydrogens. And this is known as but-1-ene because the double bond is between carbon number 1 and carbon number 2. Now the second isomer I can have is I still have my 4 carbons, but instead of the carbon-to-carbon double bond between 1 and 2, I can now put it between 2 and 3. Again, I fill in my hydrogens, and you can see that this is now a different structure. And this one is known as but-2-ene because the carbon-carbon double bond is between number 2 and number 3. And lastly, I can take one of my carbons from the middle and put it as a side chain. So I have my 3 carbons and my side chain goes there. And then one of my carbons in my centre has to be the double bond. It doesn't matter which one, it's the same molecule. So I'm going to make it this one as my double bond. And again, I add in my hydrogens, making sure that I have 8 and that each carbon has 4 bonds. And this is known as 2-methyl propane. Each of these has a molecular formula of C4H8, but you can see that they are all different, so we call these isomers. Again, we'll talk about this in a little bit more detail and give some more examples when we get on to topic 4D for the alkenes, but it is strongly advised to practice drawing out these molecules because they do come up in exams quite a lot. So when it comes to hydrocarbons, there are 3 key reactions that you have to know. Some you'll have met before and some will be new to you. So we have combustion, substitution, and addition. We're going to summarise them here, and you'll go over them in more detail when you look at each of the alkanes and the alkanes topics. So if we start off with combustion, a fuel is a substance that when it burns, it releases heat energy. And you'll have met this back in Key Stage 3. And the burning of fuels is known as combustion. And this is basically the reaction with oxygen, and it involves a flame. And there are two types of combustion. There is complete combustion and incomplete combustion. So the complete combustion of a hydrocarbon is when you have excess oxygen, or more than enough oxygen for the reaction to take place, and we're going to form carbon dioxide and water. So for example, we can write an equation for the complete combustion of methane. So methane is CH4, and it has the state symbol of a gas. We react it with oxygen, which is O2, because remember it is diatomic, and that is also a gas, and we form carbon dioxide, which is CO2, which is a gas, plus water, H2O, and that is a liquid. Now, of course, at GCSE, we are expected to be balancing any chemical equations, and when it comes to organic equations, we follow the same steps, and it's actually quite simple. We start with the carbons, then we move to the hydrogens, and then we finish with the oxygens. So if we look at the carbons first, we have 1 on each side, so they are already balanced. The hydrogens, I have 4 on the left-hand side, and I have 2 on the right-hand side. So I need a coefficient of 2 in front of the water. That now gives me 4 hydrogens, and that's balanced. For the oxygens, what you do is you add up how many you have, and then you divide it by 2, because the oxygen is diatomic. So I have 2 oxygens from the carbon dioxide, and 2 oxygens from the water, which is 4, and then divide that by 2, gives you 2 molecules of oxygen. And that's our complete combustion. Now, incomplete combustion is when we have insufficient oxygen, or not enough oxygen in order to fully react. And the thing that is the difference here is that this time we're going to make carbon monoxide, or maybe even carbon in the form of soot. We still make the water though, that hasn't changed. It's just that we went from carbon dioxide to carbon monoxide. And again, we can write an equation for this. So I've got CH4, which is a gas, plus the O2. And then this time I'm going to make CO, which is a gas, and then H2O, which is a liquid. And again, I check my balancing, so I have 1 carbon on either side. I need a 2 in front of the water to give me my 4 hydrogens. And then for my oxygens, I get 1 from the carbon monoxide and 2 from the water, which gives me 3. If I divide that by 2, I get 1.5. For diatomic substances, you can have half, so you are able to have a fraction, but this is the only time that you can have a fraction, when you have a diatomic molecule. So you can see that we are reacting with not enough oxygen here. We only have 1.5 moles as opposed to the 2 moles that we have with complete combustion. Now, the second type of reaction is called a substitution reaction. And a substitution occurs when an atom or a group of atoms in a molecule are replaced by a different atom or group of atoms. So for example, we have got methane, which is CH4, reacting with bromine, which is our Br2. And what happens is this hydrogen here is replaced by this bromine atom. And we form something known as a bromoalkane. And then we form hydrogen bromide. So you can see that the hydrogen and the bromine atoms are switching places. So they're being substituted. And the bromine is moving on to the organic molecule with the carbon, and the hydrogen is moving to bond with the bromine. And you will cover this in more detail when you look at the alkanes topic. The last type of reaction is an addition reaction. So addition reactions are going to add atoms or groups of atoms without removing anything, and this time we get one product being formed. So you can see that this time we have got an alkene, in this case ethene, and we are reacting it with bromine, which is our Br2, and what's happening is we're breaking the double bond and we are adding the two atoms of bromine, and this time we are forming something called a dibromoalkane. Di meaning that I have two bromines. So in this reaction, the two bromine atoms are adding onto the alkene to make one product, and you will cover this in more detail when you look at the alkenes topic. So we're going to finish up with some past paper questions. So the first one is talking about decane. So decane is a hydrocarbon found in crude oil, and we have the structure. And we want to explain, first of all, why decane is described as a hydrocarbon. And that is a 2-mark question. And it is because it contains carbon and hydrogen, and that keyword only. And that is where we get the second mark. So the first mark comes from saying we have carbon and hydrogen, and the second mark comes from specifying that it is only those atoms. And then the molecular formula for decane, we count the number of carbons and the number of hydrogens, and we get the answer of C10H22. And that's for 1 mark. And there you can see the mark scheme for those. We're then going to look at the homologous series. So all the alkanes in a homologous series have the same general formula, and we want to state 2 other features of a general formula. And there are 4 possible answers here. So we're going to have similar chemical properties. Of course, general formula has already been mentioned, so we can't have that. We can also say that they have the same functional group. We could always say that they have a trend in their physical properties. Or lastly, that each member differs by CH2, meaning we're going to add in CH2 each time we are moving through the different members of the homologous series. Any 2 of these would get you your 2 marks. Then we want to look at what is an isomer. So isomers, this is always a 2-marker split into 2 parts. So it's molecules with the same molecular formula, and that's your first mark, but different structural, or you could even say displayed formula. And that's where you get your second mark from. So the first part is about having the same molecular formula, and then the second part being your different structural or displayed formula. And then in the table, we want to draw the displayed, so meaning all the atoms and all the bonds for the 2 alkanes with the formula C4H10. So when you get an isomers question like this, the first thing that you want to do is just put all the carbons in a row. So we have 1, 2, 3, 4. And then I'm going to add in my hydrogens, making sure that every carbon has 4 bonds. And that's my first displayed formula. My second is then to take those 4 carbons and reduce the chain length, and we're going to reduce it to 3. I then have to put that extra carbon on as a side chain, in this case a methyl side chain, and remember the chains cannot go on the first or the last carbon, they cannot go at either end, or else we're drawing the same molecule. So it has to go in the centre here, and it doesn't matter if it goes at the top or the bottom, it is the same molecule. And then we just again add in all of our hydrogens until every single carbon has 4 bonds. And there we have 2 molecules that are both C4H10 but they have different displayed formulas. And although the question doesn't ask for it, you could also name them. And this is butane and 2-methyl propane. And there you can see the mark scheme for those questions as well. That's everything for topic 4A, Introduction to Organic Chemistry. I would strongly suggest that you get some practice questions from your teacher or the textbook of drawing and naming hydrocarbons, and also being able to draw out isomers and practice that. You can find lots of questions on the internet as well, and you can look at some past paper questions. If you do have any questions about the content of this video, please feel free to leave a comment below, and we hope to see you back soon.